equation over very simple boundary conditions. The other research direction in this area, the other method to address the control of distributed parameter system is via indirect control, when we use a reduced order model of the system as the basis for control and optimization. This method that can be actually can be applicable to a linear and nonlinear system can be exemplified. The research direction in this area can be exemplified by model decomposition, singular function, approximate inertial manifold, and empirical basis function to build the required reduced order model for the controller design. The advantages of using such indirect control strategy over the direct control strategy based on the governing partial differential equation is the low CPU cost. Since when we are using a model approximation of the system instead of the governing partial differential equation, it could be easily implementable for real-time optimization and control. And I already actually discussed that this method could be applicable to more complex nonlinear system over irregular boundary conditions. But the only problem with this type of control methods to address the control of distributed parameter systems is the approximation error complexity that I'm going to discuss in the first part of this talk, and I'm going to show you how we could improve the approximation accuracy during the process evolution. Consider the partial differential equation of the order n in this abstract, nonlinear, general input affine form. We could actually, for the control purposes, we need to define two types of measurements. The first one is the continuous point measurement sensors, which is just like a regular measurement to measure temperature and concentration, which is fixed at a spatial location of the, for example, column. The second actually type of measurement output that we require is the periodic distributed measurement sensor, variables, which this type of measurements must be distributed alongside the column, for example, column or reactor lengths. Such measurements could be identified, could be obtained by a spatial distributed fixed or moving sensors using, could be estimated by in parallel high fidelity simulation if we do not have enough sensors to capture the spatial variation, and could also be estimated by a PD based dynamic observer. So this, we could define a control output where it's important, which variable is important at which specific location to be controlled. For example, concentration and the outlet stream of the reactor, or the temperature at the hot spot. Over a general form of the homogeneous boundary condition and initial conditions. So the important property of dissipative partial differential equation is that we could decompose the infinite dimensional representation of this type of system into two different categories. A finite dimensional approximation, which could possibly be unstable, and a finite and an infinite dimensional fast and stable subsystem. And we could use a slow and possibly unstable subsystem as the basis for controller design. Since in all of those cases, when there is actually a major separation, we could capture the long-term dynamic behavior of the slow subsystems, and it could represent the complete dynamic behavior of the original partial differential equation. Yes?
Small question. So
yes.
I don't have quite the intuition, but why finite dimensional slow will be unstable?
Oh no, it could be possibly unstable. So for example, for general unstable processes, all of the unstable modes, when we characterize such decomposition, belongs to a slow subsystems. Okay. That's the nature of dissipative partial differential equations. Okay. So assume that I will actually show you a simple example how you could identify those modes and use the important modes for the control design. Okay. But specifically for the dissipative or parabolic partial differential equations, when you solve the eigenvalue problem, you could actually find a big separation between the value of the eigenvalues that indicate the separation between the governing subsystems.
Okay.
Okay. This concept can be implemented easily, as you all, most of you know, using Galerkin projection. Just assume that we could decompose the spatiotemporal pattern. This x could be temperature concentration that varies in a spatial coordinate and also temperature. That could be decomposed into an exactly a spatial form and a dynamic form. So when the number of n increases to infinity, the inequality converts to equality, of course. But how to implement such a type of a strategy and decompose the modes? If you have the general partial differential equation in this form, by actually replacing the value of x by this approximation and taking the Galerkin, taking the integral projection over the entire domain with respect to the phi star, we could obtain the dynamic behavior, the reduced order dynamic behavior of the system in the form of finite number of ordinary differential equations. But the important question here is the shape and the optimal number of basis functions required for such discretization. For most of the cases, they just actually use just the periodic basis functions for such discretization, but that's not an optimal case. So the basis functions for this system discretization are generally the solution of the nonlinear dissipative eigenproblem, which originates from the eigenproblem here. So, just actually, I just want to take an illustrative example to show how it works. For example, for the illustrative example that we consider here is a tubular reactor with a cooling jacket when an irreversible exothermic reaction takes place. We consider the temperature dependency in the reaction rate, and we are manipulating the variables by the cooling jacket and feed temperatures. These actually are the general form of nonlinear partial differential equation which could describe the spatial temporal dynamics of temperature and also concentration in this simple reactor, subject to the boundary conditions and initial condition. By using actually dimensionless variables and homogenizing the non-homogeneous part of the boundary conditions inside the PDEs by introducing the delta functions, we could get a dimensionless form, homogenized partial differential equation in this form, where we could actually solve the eigenproblem for that. For most of the cases, the researchers only actually just avoid the nonlinear dynamics of the spatial differential operator and solve it for a linear eigenproblem to get those basis functions. But it's not accurate for most of the chemical engineering cases when the reaction is dominant. So we could actually, by solving that eigenvalue problem for a linear case over simple boundary conditions, we could obtain the basis function by the solution. But most of the time, the eigenvalues are not in an explicit form, so we may actually solve a nonlinear equation to obtain those eigenvalues. And these are the eigenvalues that dictate the decomposition. For example, when we obtain those eigenvalues and we order it by size, for the dissipative PDEs, there is always a big separation between the slow dynamics, the slow eigenvalues, and the fast eigenvalues, where the slow eigenvalues could be also positive. That may actually describe the instability in the original system. So as I actually discussed in the previous simple example, the analytical method cannot be used broadly for this type of application. Since to apply the analytical method, there may exist some significant nonlinearity in the differential operator. For example, So for example, in this actually illustrative example, we had the nonlinear terms as the nonlinear reaction terms that makes the problem nonlinear. And when the actually, in the presence of unknown parameters or the complex boundary condition, we also could not apply such analytical techniques. One alternative to bypass this problem is using numerical methods. But such numerical methods could not be applicable to the system with unknown dynamics or unknown parameters. For example, if you want to solve the nonlinear eigen problem using the numerical methods, if you do not have the value for the parameter of the system, there is no way to compute those based on the numeric techniques. So an alternative to bypass these difficulties is through using statistical methods. So just assume, instead of actually solving those eigen problem, you're collecting data from the system. By the data, I mean spatiotemporal data. Each of those spatial profiles, you could actually see the z direction and also t specified at a specific time, which we call snapshots. Just assume that you are actually taking a picture of a system. You have the spatiotemporal profile of the temperature at time t1, time t2, to time tn. You collect that before the process starts, and by actually collecting more data, you could get a more accurate set of basis functions by employing the principal component analysis method like proper orthogonal decomposition, K-mean clustering, or other machine learning techniques. But actually the important problem here is that if you want to do it offline, there is some situation regarding the dynamic behavior of the system that may not be captured in offline calculation. For example, you could not actually find a sufficiently small number of n for which you need actually the number of spatiotemporal profile to get a more accurate basis functions. So there is actually a need to revise those basis functions during the process evolution based on the data from the system. So if you could build such adaptive kind of revision of the basis function, you do not even need the a priori availability of the sufficient large number of data points before the process starts. You could just actually initialize such basis functions based on a very finite dimensional set of data and revise those basis functions as needed during the process evolution for the control purposes. As I said, for the offline statistical approaches, we always need a priori availability of the solution data which captures the real dynamics of the system. But using those revisions, we could actually avoid that property. So based on this idea, we developed an algorithm to recursively revise the set of empirical basis functions. This algorithm briefly actually has two major components, the offline step and the online step. The offline step, just like the regular proper orthogonal decomposition, we gather the spatiotemporal data, compute the covariance matrix, identify the dominant eigenvalues and the corresponding basis functions, and use that as a basis to initiate the closed loop operation. And then during the process operation, when the new data becomes available from the system dynamics, we revise those empirical basis functions based on considering the overlap between the fast and slow covariance metrics representing the dynamic of the system. Even actually using this strategy, there is still two important questions that has not been answered. The first question is, when we need to revise those basis functions? That's the first unanswered question. For linear system, we use the duality between such reduced order model revision frequency with the desired feedback frequency in control network system with communication constraints, and we use the same strategy in network control for the linear system to compute the minimum number of revisions required by a linear system before the process starts. For the nonlinear system, it's more complex, so we couldn't actually do the offline calculations. Instead, we could do some online monitoring. The way that we propose to address this revision problem is minimizing the demand for the reduced order model revision by monitoring the control Lyapunov function. So we monitor the candidate control Lyapunov function. When it starts to increase, that's the time that we need to revise our reduced order model based on the snapshots from the system. The increase in the Lyapunov, in that case, since the controller is stable, means that the model that has been used for the controller design is missing some dynamics. The second important question that must be answered at this point is how we collect those snapshots for a computationally efficient revision of the basis functions. So to actually handle this computational cost in real time, we decided to fix the number of snapshots at the same time when we are doing the calculation. Since in the first strategy, when the new snapshots becomes available, we throw out the oldest one and keep the new one, and this window actually moves through time. But using this type of strategy, we may miss some important snapshot as the process evolution goes. For example, at the beginning of controlling a nonlinear process, we have a loss of fluctuation. But after a finite number of time, when it goes to the steady state value, those fluctuation disappears. So that means if we use this simple technique, when the controller actually passed the transient behavior, we could not keep those important information contained inside the reduced order model. Since we are repeatedly actually throwing out the oldest one and keeping the newest one that may not actually contain enough information to represent the system. So for such cases, when we have a disturbance in the middle of actually that's a stable behavior, the controller is not aware of the disturbance until he could get feedback from the process. But using an alternative strategy, we could always keep the most important snapshot. Instead of actually keeping the newest one and throwing out the oldest one, we keep the newest one, do a least informative snapshot identification, and this time, instead of actually throwing out the oldest one, we throw out the snapshot that contains less information. We use actually a Shannon entropy theory and Shannon entropy measurement to compute, to actually identify the information content for each of those snapshots. Based on the proposed model order reduction methodology, we built a supervisory supercontroller structure. As you could see, this is actually the process, just like the regular flowsheet. We assume the availability of two types of measurement sensors: the continuous point measurement sensor, which is typical in all of the chemical plants, and the periodic distributed measurement sensors to capture those snapshots. But these periodic distributed measurement sensors could be replaced by high fidelity simulator or by a PD observer, which could generate those snapshots for us instead of actually capturing from the real process. Then we actually use those snapshots to build a reduced order model in this actually nonlinear ordinary differential equation with finite dimension. And we revise those reduced order model during the process evolution by monitoring the control Lyapunov function. When the control Lyapunov function is increasing, it means that we are not capturing the dynamic of the process, the general dynamic correctly. So we need more snapshots to revise our reduced order model and get a model which is suitable for controller design. We use a dynamic observer in the Lumberger type to estimate the state value of the system which are not accessible at the operation. For example, to estimate the concentration which may not be accessible during the process evolution based on the information from the temperature sensors. We also used a parameter estimation layer, a system identification layer, via combining it with controller via Lyapunov-based indirect adaptive control to identify the unknown parameter of the system using actually by defining the Lyapunov function over the error of the estimated parameters. And then we actually develop a nonlinear controller to handle the closed loop performance, which guarantee the closed loop stability. Based on the proposed adaptive model order reduction methodology, we actually developed some framework for output feedback control, geometric output tracking, controlling the presence of network communication constraints, We used it for spatiotemporal dynamic shaping, and we also use it for the system with unknown transport reaction parameters by taking advantage of two-layer adaptation, one layer to revise the reduced order model required for the controller design, and the other layer for estimating the required parameters for the controller design. We implemented such methodology to some benchmark distributed parameter system like the fluid flow systems, plug flow reactor, and fixed bed catalytic reactor. For this presentation, I only consider a simple illustrative example, the Chromatosy-Washinsky equation as a benchmark, which used in the fluid flow industry to describe the falling liquid film on a stable frame front and so on and so forth. These are the equations. So the objective here is by actually manipulating the flow in these liquid jets, we are the desired property is having a flat gas surface. So we could actually define the deviative variable from the state reference, and we could actually have the controlled Chromatosy-Washinsky equation subject to the periodic boundary conditions. In this study, we only actually use one continuous point measurement sensor at this location. We consider 6-point actuator, which are the liquid jets in the wall at these actually locations. At the beginning of process, we consider the 2 seconds to collect the required snapshots to initialize the reduced order model required for the to design in the controller. And during this actually the open loop time period, the control is inactive. So we manage the proper orthogonal decomposition to capture 99.9% of the total energy of the ensemble, and we also monitor the control Lyapunov function for on-demand revision requests. We use the POD-based model for the controller design, but for the real process, we use a high-resolution discretization using the finite difference to make sure that it will work in the presence of uncertainty between the approximate model, which is used for the controller design, and also the real plant. These two figures shows the spatiotemporal profile of the state variable in open loop. So you actually could see the spatiotemporal profile and the second norm of this second spatial norm that you could see that converges to the steady state value. And this figure shows the closed loop dynamics. For the 0 to 2, the control is not active until this point, and then the control is activated. Since in this actually open loop period, we are collecting the snapshots to initialize the control structure. And as you could see, it works perfectly. So the spatiotemporal profile goes to 0, which was actually the desired for the wave motion separation. This figure shows the initial set of basis functions, which are derived based on offline proper orthogonal decomposition during that 2 seconds process, open loop process operation. This figure shows from when the control is activated as t equal to 2 to 12, the number, the actual dimension of the reduced order model. As you could see, during the time evolution, the structure of the reduced order model will change based on the revised basis functions. These figures also shows the values of the six manipulated inputs. As you could see, obviously, for the first 2 seconds of the process, the control is inactive to collect the required data. And this figure shows the monitored control Lyapunov function. As you could see, at some points, we could actually detect the increase. But this increase, since actually we are periodically revising the reduced order model, that will not affect the stability criteria. So this figure shows at the time that we require those revisions, since we are actually using an on-demand model order reduction methodology. And this actually shows the required basis function at those 4 time instants. As you could see, the shape and the number of basis function changes, and we only request the basis function revisions at a specific time when we really actually need those. To summarize the first part of this talk, I actually introduced you the control of distributed parameter system via adaptive model order reduction. We revised the reduced order model on demand to reduce the required computational time to implement the controller. And we use the reduced order model as the basis for the controller and observer design. This actually type of methodology results in 10-fold reduction in computational time compared to using finite difference for to discretize the partial differential equation and use it as a basis for the controller. And when we compare our methodology with just the traditional recursive proper orthogonal decomposition, it results in 3-fold reduction in computation time. The important issue here is, as you may recognize, the controller was designed based on the nonlinear control methodologies. So such actually type of Lyapunov-based controller is very limited to dimension of the system. So we could practically, theoretically, we could use it for any type of system with different dimensions. But practically, when you want to generate those Lyapunov functions and obtain the control laws, you could only analytically could do it for the systems consist 2 to 5 or maximum 10 number of states. For the so this actually nonlinear control methodology is not suitable for large scale system when we have 200, 1,000 or 10,000 number of states. So then an alternative to bypass this problem is using optimization-based control methodology, which is the subject of the second part of this talk. Optimization-based control methodology, like model predictive control, have been widely used in academia and industry to address the control of large-scale problems. However, finding a right control paradigm is not straightforward. Obviously, we have a centralized control architecture to consider. This is a very promising perspective for large-scale systems. However, there exist some challenges regarding the implementation when the size of the system increases. The other extreme is fully decentralized control architecture, when there is no communication between the local controllers. This very old perspective has been widely used in industry, but for most of the cases, it will lose the stability and acceptable performance where the system, when we have a highly interactive system due to the tight material and energy integration. So in the middle, distributed optimization-based control methodology could bridge the gap between fully decentralized and centralized control architecture by taking advantage of different level of information sharing and cooperation between the local controllers to compute the required manipulated inputs. Distributed model predictive control have been widely actually used in industry and academia, as I actually discussed in the previous slide. A lot of research work has been done in the area of distributed model predictive control, but they mostly focused on the on identifying stability criteria, performance evaluation, and introducing communication pattern like sequential DMPC and iterative DMPC. When the sequential DMPC, there is a sequential flow of information between local controllers. It means that each local controller, to handle the control problem for a specific part of the system, must wait for the previous controller to actually compute the manipulated inputs and then get those information to compute their own manipulated inputs. However, in the iterative distributed model predictive control, we could take advantage of parallel processing of local controllers and actually for example, solve the dynamic optimization problem at one setting, and then share information and repeat those dynamic optimization problem until the convergence. So we could actually take advantage of using parallel processing for this type of control architecture. The research work in this area also introduced a different level of cooperation between local controllers. But the important subject which is missing in this direction is the impact of system decomposition, which has not been studied in DMPC implementation. which is a very important subject. Why? If we have an optimal decomposition of the subsystem, as a conclusion, we have an optimal number of local controllers for DMPC structure. It means we could distribute the output variables and manipulated inputs among the network of local controllers and reduce the interaction between the local controllers. That's a major part of the computational load for iterative DMPC. And we also could minimize the DMPC computational time, as I actually described, through such reduced communication. In our work, we focus on comprehensive study of decomposition effects by monitoring the closure performance and also the computation time. We use different network decomposition methods. We also use different communication protocols, sequential, iterative, fully decentralized. We also consider different level of cooperation between local controllers. And by different level of cooperation, I mean when the local controllers share the same objective function for the dynamic optimization or use the different objective function. And we also actually use different dynamic optimization platforms from sequential quadratic programming to IP-opt in the presence of measurements noise effect over a wide operating range. I actually choose this benchmark to show the effectiveness of the proposed distributed control methodology. It's actually a typical process which has been widely used to implement distributed model predictive control methodologies in the literature. Consists two CSTR and one separator unit with a recycle stream, where two series first order reaction in this form take place when B is the desired product. We consider 9 manipulated inputs, the feed flow rate, the midstream flow rates, and also the heat flows to these 3 units. We also consider 9 output variables, the hold-up dynamics in each of those units, the temperature, and also the concentration of the desired product. If we have the process model in this general nonlinear input affine form, we could actually formulate the centralized model predictive control problem by repeatedly solving the dynamic optimization problem subject to the objective function, which penalizes the tracking error and also magnitude of the manipulated input, subject to the process model, the lower and upper bound on the decision variables, and also the inequality and equality constraints which represent the desired performance of the system. So if we have an optimal decomposition, or if we have any decomposition, we could break that centralized control problem into a smaller control problem that can be solved in parallel. And then share the information. By sharing the information between the controller, we could actually obtain the convergence of the centralized model predictive control architecture. So in this case study, we consider 15 number of sampling in the prediction horizon to solve the dynamic optimization problem. The sampling period is considered to be 3 minutes. Then the prediction horizon for solving the nonlinear dynamic optimization problem is going to be 4 to 5 minutes. We consider 6 hours closed loop process operation, where at each 2 hours we have different tracking zones. So by manipulating the system variables, the desired variables changes during those tracking zones. So the controller need to track those desired outputs. We consider a variety of cooperative and non-cooperative architecture, but to summarize, when we compare the cooperative and non-cooperative, the non-cooperative control architecture has the same closed-loop performance with the cooperative for these simple cases. However, it requires less computational time. So we also compare the sequential and iterative information flow, and they both result in the same closed-loop performance, but using the iterative control architecture, we obtain a less computational time to operate the nonlinear DMPC problem. We also compare different decomposition based on the community-based, relative sensitivity array, intuitive decomposition, and also other decompositions. And we use different dynamic optimization platform method, as I actually mentioned earlier, and we resolve that using the IPO, interior point optimization, in the best way to solve such underlying dynamic optimization problems. We consider a large number of different decomposition, as I actually mentioned earlier in the previous slide, but out of all of those more than 10 decomposition, I only actually choose 3 beside the centralized, which had the best closed loop performance. The first one is the centralized model predictive control. When there is no decomposition, there is no subsystem, we are actually solving the dynamic optimization problem over the entire plant. But for these 3 decomposition, which were actually more suitable for this example, there is actually subsystems for which subsystem we require to design the distributed controller, when the distributed controller could communicate over the network. The first actually decomposition method was the input-output bipartite graph, which is developed in our group. The second one is also optimal communication, which is also a result of our group. And the fourth one is just choose the intuitive decomposition based on material and energy balance to compare the closed loop performance of those decomposition. So I want to introduce you how we do those decomposition. I'm going to focus on the optimal community-based decomposition, since I will actually show you in the next slide which has the best performance. First, actually, I want to introduce you to the graph representation of the control system. It means if you have a nonlinear control system in this general input affine form, you could actually obtain an equation graph for the system which connects the input variable to the state variable and output variables, where the connect edges in this graph mentioned the direct influence of, for example, this controller on this specific state. Then there is actually a duality between the minimum pass from one input variables to the output with the relative degree concept that we defined in the nonlinear control concept. So by representing the whole nonlinear control system as an equation graph, we could use network theory to identify the optimal decompositions. So the way that we propose to handle this problem, the objective is having a strong intra-community and weak inter-community connectivity. And the method that we used for this decomposition for the community detection was through modularity maximization, when we are trying to identify modular decomposition. So the modularity index could be defined as a fraction of intra-community edges observed in an existing graph, which is optimal at the actually end of the iteration compared to the random graph. By using such decomposition technique, when we design the controller, we already minimize the required interaction between the controllers, which minimizes the required interaction between the local controllers. So when we minimize the interaction between the subsystem, we will need actually a minimum minimum interaction between the local controllers. For this specific system, this is the shape of the equation graph, which indicates all of the input variables, output variables, and the state variable of the system. And using this optimal community-based decomposition, we obtain 3 subsystems. So this may seem obvious, since actually it's very close to the optimal decomposition based on the configuration of the units. But actually, for the more general cases that I will show you, actually in the next cases, it's not obvious at the beginning. So to compare the closed loop performance of distributed model predictive control using this decomposition, we introduce a performance index, which consists just like a regular objective function, the tracking error, and also the penalize the magnitude of the manipulated inputs. And different colors, yellow, red, and blue, shows different tracking zones from 0 to 2, 2 to 4, and 4 to 6. As you could see, the best performance belongs to the centralized, obviously. But the DMPC, based on the optimal decomposition, has a very close performance to the centralized as a result of the optimal decomposition of the subsystem, which minimizes the interaction between the local controllers compared to the other actually decompositions. Okay. We also actually consider, compare the results in the presence of measurement noise, and we got actually the same conclusion. So we also, beside that is the performance index, the other factor which is important is the required computation time, which we are going to focus, since we are inventing such distributed model predictive control compared to centralized one to reduce the computational effort. If you consider the computational time overally and over also different tracking zones, you could actually compare the decomposition tree, which is based on the community-based decomposition, compared to the other decomposition and also the centralized, and you could actually easily see this a significant reduction in the required computational time, which makes it implementable for real-time optimization and control. We also actually check the results in the present of measurement noise. We almost get actually the same results. At least the order of the decomposition were the same. This figure actually shows the actual state variable of the system, the hold-up dynamics, the temperature dynamics, and also the concentration of the desired products. When for each tracking zone we have different desired value, as you could see, the controller could actually force the state value of the system to track the desired outputs in hold-ups, temperature, and also the concentration. This figure also shows the temporal profile of the control variables in the discrete form, since actually it's a model predictive control problem for the first tracking zones from 0 to 2 for all of the 9 manipulated inputs, second tracking zones, and third tracking zone. As you could see, I represent those manipulated inputs in a deviation from the steady state. As you could see, as time evolves, the manipulated inputs converges to the steady state values. We actually provide a comprehensive study to evaluate the effect of system decomposition on model predictive control. To summarize, we consider different communication protocols, sequential and iterative, which is actually the best two ways to communicate. And also, we also consider fully decentralized, which has the worst performance. We also consider different levels of cooperation between local controllers, different dynamic optimization platform in the presence of measurement noise and wide operating range. And we analyze the closed loop performance and the computational time to identify the best control architecture, and we implement the proposed framework to a benchmark integrated process system, which was a reactor separator case, and we identified that iterative DMPC using optimal community-based decomposition is the best distributed control architecture, which has the performance very close to the centralized model predictive control, but it could significantly reduce the computational time or order of 10 or even actually 20. So to further extend the applicability of the proposed control strategy, we implemented to a gas sweetening process. The gas sweetening process refers to a group of processes that use amine-based solvent to remove hydrogen sulfide and carbon dioxide from sour gases. It's a common unit process in refineries, petrochemical plants, and natural gas processing. It contains reactive adsorption of sour gases, regeneration of solvent using steam, characterized by tight material and energy integration, which makes it too complex for optimal operation and control. And very little work in this area has been done on the model-based control of amine gas sweetening plants, and most of them only focus on very specific configurations. We actually, in this study, we focused on a two-stage amine gas sweetening plant, which is of interest of our industrial collaborator in Abu Dhabi National Oil Company. The process that they are currently have, and they are going to implement this method, is a two-stage amine gas sweetening plant. As you could see, when we could actually, if you could you actually recognize the colors? The red color I used for the amine stream, the green I used for the steam stream, and the black I used for the gas stream that needs to be from which we need to remove those sour gas components. We consider 6 manipulated inputs. 2 of them are the inlet gas at stream temperatures, and 4 of them are the solvent and stream flow rates between different columns. The control outputs is considered to be the gaseous content of sour gases leaving both absorber stage, where one of them actually, for example, in here, Y1 denotes the concentration of the CO2, and Y2 denotes the concentration of the H2S. To model the system, we consider a mass transfer control, adsorption and desorption. We consider two-film theory by considering the resistance to mass transfer on both liquid and gas sides. We consider the temperature dependent mass transfer coefficient and driving force. We also consider the heat effect of the mass transfer to model the system more accurately by neglecting the loss of water and amine in the columns. This actually a slide shows the model equation for the 4 columns and also the 2 heat exchanger. It consists 28 partial differential equations in their general nonlinear form, when the nonlinearity comes from the equilibrium constant and also the equilibrium pressure. And we also actually, as I actually mentioned earlier, we also modeled the equation for the 2 heat exchanger for the hot and cold stream. So totally we have 28 number of partial differential equations which must be solved in real time. By taking advantage of such optimal decomposition for this specific system and extending the equation graph representation for the system of partial differential equations, this is the result for the optimal decomposition using the community-based control, community-based architecture, which minimizes the interaction between the subsystems. It's not an obvious decomposition. Somebody may think that we may control each of those single units by its own, or we may only consider absorbers together for the control setting and also the strippers together for the control setting. But the thing that dictates this type of decomposition is that majority of the reaction are taking place in the amine streams. So we use the finite difference to discretize the partial differential equation. We describe the real process by high resolution discretization, and which results in 486 states. But for the controller design, we only use a reduced, a low resolution model which consists 234. So there is actually a mismatch between the real process and also the model that we consider for the controller. We consider 8,000 seconds closure process operation and 5 number of sampling in the prediction horizon. The sampling period that we consider is equal to 320 seconds, which results in the 1,600 second prediction horizon for solving the dynamic optimization problem. We actually do all of the calculation in MATLAB 2015 using 3.4 gigahertz Intel Core i7 processor. We employ the interior points optimization to solve the underlying dynamic optimization problem, and here are the results. As you could see, I mentioned earlier that we considered 8,000 seconds for the closed loop process operation, which was the required time for the open loop system to be stabilized. But here, using actually the distributed control architecture, you could actually have the stabilization around 1,000 seconds, which is actually perfect. This actually figure shows the output variables of the system that needs to be controlled in the deviation form from the steady state value that converges to 0 as time evolves. And this figure shows the temporal profile of the manipulated inputs. Just to make sure that is the best candidate for the distributed control architecture, we compare distributed MPC based on optimal decomposition to the centralized MPC, to the distributed MPC using a different decomposition, and to the decentralized MPC using the same optimal decomposition. So this figure actually shows the performance indices. As you could see, distributed control using optimal decomposition is even having the better performance compared to centralized. Since the original dynamic optimization problem was non-convex, through such decomposition, somehow we could get a better minimum. And this figure actually shows the required computation time for the implementation. And as you could see, the decentralized control architecture, of course, has the better computational, has actually less required computation time. However, when we consider the performance index, it results in using distributed MPC using optimal decomposition. So just to summarize, we developed a detailed dynamic model of a two-stage amine gas sweetening process. We used it as we used a community-based decomposition to obtain the optimal decomposition. We implement nonlinear distributed model predictive control, and we compared the closed loop performance and computation time of optimal distribution model predictive control to alternative control architectures for just a benchmark and also a real process. And a distributed control framework of this kind can be extended and can be easily applied to any large-scale chemical plants, which is actually the subject of my future work. So in my future work, I'm going to combine the network analysis for the optimal decomposition, the optimal control in the form of distributed model predictive control, the system identification to identify the required unknown parameters of the system or the controller design, and also the data analytics to improve the reduced order model required for distributed parameter systems required for the controller to design for distributed parameter systems. And the future application that I'm considering is the energy system and biological systems. For the energy system, I'm interested in applying such control methodologies to combine cycles like polygeneration units when we produce the advanced materials and chemicals and energy at the same time. As you may know, this type of process are very famous for having a very intensified integrated dynamics that makes the control problem very interesting. The other application that I'm looking for is using the same control methodology for the model predictive chemotherapy. Just assume that you have a multi-scale model of the human body, which could be where you could actually increase the accuracy of the model by inducing the clinical database correlations. You could use the same control methodology, even distributed control methodology, to compute the optimal dosage of the chemotherapeutic agents, which minimizes the pain, the growth rate of the tumor, and it could be actually easily used instead of actually just the regular intuition methods that the cancer specialists and oncologists actually use in treating cancer. At the end, I would like to thank my advisors and collaborators, Professor Antonis Armao, my PhD advisor, and Professor Rob Rio, Professor Dion Vlachos at University of Delaware, and Professor Prodromos Dautidis, my current postdoctoral advisor at University of Minnesota, Professor Ali Mansouri from the Petroleum Institute, and Ventao Tanya Manjiri Moharir, my colleagues at University of Minnesota. And I want to thank the National Science Foundation, Catalyst Center for Energy Innovation and University of Delaware, DARPA, Department of Energy, Office of Science, Office of Basic Science, and of course the Petroleum Institute for the financial support. Thank you very much for your attention, and I'd be more than happy to answer any questions.
Excellent presentation. So, any question?
Thank you for the presentation. I would like to ask, how do you quantify the objective function when you decompose the system? Is it based on the interactions?
The objective functions, you could actually generally design the objective function. For example, when you do those actually optimal decompositions, as a result of those optimal decompositions, you have a cluster of input and outputs. So for example, if you have 6 manipulated inputs and 6 control outputs, U1 and U2 belongs to the same community that Y1 and Y6 belongs to them. So based on those 3 values, we define the objective function in the non-cooperative architecture. But for the cooperative architecture, all of those local controllers share the same objective function.
I have 2 questions. First, if with the optimization approach that you mentioned later, if you would have any risk of overfitting the controller, and
What do you mean by overfitting?
You see, I'm not sure if this is a problem with controllers in general, just because it sounds to me like you're trying to train a model over time on some data, right?
The model itself is, the first part of the talk was actually based on revising the model based on the experimental data as needed. But the basis for the controller is just a basic principle model. It's not a model based on data. So we're only actually using data as needed to correct the dynamics of the model, which can be useful for the controller design.
Okay.
But the model itself is not based on data. We only use the data to obtain the correlations which could improve the accuracy of the model.
Okay. And the second would be, how would this scale? I'm not sure what the size of the plants that we were.
It's a real plant. So we have actually a real plant in Abu Dhabi. So that was the interest of our industrial collaborators. So we used actually the same dimension as just a real plant. And we also, beside implementing it in, for example, MATLAB and other actually softwares, we also implemented a model in GPROMs that we are actually using that as a real process to make sure that our controller, based on the model that we developed, is working perfect through model mismatch.
Thank you.
Yes.
Small question for the second part.
Yes.
For the iterative decomposition, will the controllers all I'm not sure about this, but like will the order of different controllers adaptive order influence the performance?
Let me actually explain. I had a slide earlier. Just give me I have this infrastructure. Here. So in the iterative controller, the MPC, each of the local controllers solve their own manipulated inputs. So they actually are solving a dynamic optimization problem, a local dynamic optimization problem, and compute the manipulated inputs. After the first round of simulation, the computation time for the first round of simulation is equal to the controller that takes longer.
Yeah.
Since actually all of those optimization is actually handling in parallel. So when for example, controller 1 compute the value of the U1, during the computation, it used the nominal value of U2 to UN. But when the U2 value is computed using the second controller, then there could be a difference between the nominal value that controller first uses and the actual value that the second controller computes.
Yeah.
Right?
Yeah.
So we have a level of iteration. So in this iteration, all of the controllers share all of the information and recompute the manipulated inputs in the second run until convergence to the unified manipulated input components.
Okay, because the graph makes me
Yes.
feel like you want and like it's like
No, there is an iteration between the controllers.
It's not between the controllers.
Yes.
Like,
For example, when for a simple case studies, when you start the controller at the beginning of actually when we have actually maximum difference from the state, it requires most of the time it requires 5 to 10 iterations. But when actually the process goes, as the process evolution, so the required number of iteration decreases to 1.
okay.
Which actually makes it suitable for compared to the sequential strategy.
Any other question? I think we're close to 1 p.m. So let's give another round of applause to the excellent presentation. All right, so next week on Tip, enjoy the break, and next week on Tuesday we still have sandwich serving you for lunch.